Good day everyone, my name is Stephen Asante. Today we are going to talk about cache memory. Cache memory, they are small yet mighty hardware that lets modern CPU fly. By the end of this video, we are going to know what cache is and why we need it. Think of a cache like a top drawer of a desk. Instead of walking to the filing cabinet, which is the main memory, every time, you keep the papers you are touching most often right beside you. Formally, a cache is a small, high-speed memory that keeps copies of data the CPU is likely to reuse. So it keeps the data the CPU is likely to reuse and the one the CPU really don't need it doesn't keep it. So that's what cache is. And it sits between the CPU and the DRAM, acts as an intermediary, reducing the average time to access data from the main memory. So it helps to reduce time in accessing data from the main memory. The memory wall. Due to time, as time passes, processes have been sped up so fast that processes are more faster than DRAM. This disparity is called the memory war. Without interventions, the CPU would be idle, waiting for hundreds of cycles for each time or for each fetch. Caches creates hierarchies, fast memories close to the core bridge. So, cost-effective hierarchy. It forms a cost-effective hierarchy where smaller, faster memories complement large but slower ones. That's what the memory wall does. And this is how cache works. The CPU sends the address. The cache uses part of the address called the index to select a set. Another part to check if the needed block is present. If found, data is supplied instantly. If not, the block is pulled from the next level, stored and forwarded to the CPU. That's how the cache works. And this is the hierarchical level of the memory wall. The L1, typically 3265 kilobytes per core, split into instructions and data caches. Fastest, directly accessible by the CPU. Latency, that's the L1. Which is the L2? Larger, typically 256 kilobytes to 1 megabyte per core. Slower than L1, but faster than L3 main memory. Stores data not found in L1, that's the L memory. The L2. The L3 shared among all CPUs, ranging from megabytes to tens of megabytes, slower than L2, but much faster than DRAM, acts as a victim cache from the L1 and L2. So the hierarchical cache levels, each level backs the one before it. That's how it works. Let's see, locality reference. Cache memory effectiveness relies heavily on the principle of locality reference, which states that programs tend to access data and instructions that are spatially and temporally close to those they have accessed recently. So the locality reference programs aren't random. We reread the variables in loops, which is the temporal, and process arrays sequentially. That's the spatial. Designers exploit these patterns so that small caches capture most accesses, boosting speed without huge cost. That's the locality reference talks about. Data accessed once will likely be accessed again very soon. So if a particular data is accessed by the CPU, it is likely that it is going to access it again. That's why it is I said earlier that it's reread variables in loops. Cache organizers. A cache organizer is an array of lines, grouping lines into sets that let us balance speed and flexibility. That's the cache organizing. They verify that a line really contains the requested address, while valid and dirty bits track whether data is present and whether it has been modified. That it's like the organizer of the whole thing. It organizes everything to make it look clean and very clear. So the dirty flag, a bit indicating if the data in the cache line has been modified and need to be written back to the main memory. That's the cache organizer. The cache organization. The mapping techniques. Mapping technique decides where a memory block may live. Direct mapping is a simple and lightning fast but surface conflicts. Fully associative is flexible but expensive. The fully associative is very flexible but expensive. And the n-way set associative hybrid approach where each memory block can be placed in limit number of locations within specific sets balances performance and cost. N-way set associative split the difference between the modern L1 cache. Split the difference. The modern L1 cache are mostly often 8-way. Nice policies. So the direct mapping, each memory block has only one specific location in the cache. Simplest to implement but prone to conflict message, like I said, that a simple and lightning fast but surface conflict. The writing policy. Well, on a store, do we update the RAM immediately? We write through or but buffer until eviction, which is the write back. Write back cuts traffic but needs data tracking. Multiple processors are the challenging of keeping copies consistent, solved by protocols like MESI. MESI. They keep the copies consistent by the protocols like MESI. The write through. Data is written to both cache and main memory simultaneously. Simpler but slower due to main memory access time. So it's slower to access the main memory than the cache. That's why it gets slow. The write back, which is the buffer until eviction. Data is written only to the cache. Main memory is updated only when the dirty cache line is replaced. Faster but requires a data bill. Like I said earlier, that the write back cuts traffic but needs data tracking. Sorry, that's the simple explanation I can give. So the last but not the least, key takeaways resource. What we've learned so far is that cache, fast copy of memory. Cache memory is a critical component for high performance computing, acting as a small fast buffer for frequently accessed data. So every frequently accessed data is derived from the cache. The exploit locality. Its effectiveness is deeply rooted in exploiting temporal and spatial locality of reference in program execution. That's the locality exploit. The choices of mapping and replacement policies significantly impact cache performance and complexity. That's the mapping and replacement matter. Tune for high hit rate. Optimizing cache design aims for high cache hit rate, minimizing and dreaded memory war. So this is a little about the cache. If you want more, or if you want depth understanding, then you can check out a quantitative approach. Computer architecture. A quantitative approach is the defining textbook for in-depth understanding of cache memory and other architectural concepts. That's the book this book. This book. You can get more explanation of the cache memory over there, detailed. Thank you very much. See you later. See you next time.